So for this video, I'm going to do Lewis structures, and I'm also going to look at formal charges, and we're going to look at whether or not we need double or triple bonds, and we're going to look for exceptions to the octet rule, and then we're going to look for possible resonance. So that's the chapter 10 content. The rest of this, where we look at the geometry and the orbital hybrid, that will come in chapter 11. So I'm just looking at this first section here for this part of the worksheet, and then I'll do another video for the second part of the worksheet for chapter 11. So first thing is we have a compound N2O, and we want to do the Lewis structure. Now, normally, I put this one on here on purpose, normally whatever we have a single of is what we put in the center, and then the multiple would go on either sides, but this is an exception. When I look at my periodic table, oxygen is more electronegative than nitrogen, so it shouldn't be in the center. The nitrogen is less electronegative, so actually the nitrogen will go in the center. So we're going to start with a skeletal structure of NNO, right? N being in the middle. So that's my skeletal structure. I always go and then look at the valence electrons next, so VE for valence electrons. Each nitrogen brings in 5, so there's 2 of those, so that's 10. And then oxygen brings in 6, so I've got 16 total electrons to work with. I've used 4 in those 2 initial bonds, and let's look at how many left we have and then how many we need to complete the octet. So the nitrogen on the end has 2 electrons, would need 6 more to get to 8. Nitrogen in the middle has 4, needs 4 more to get to 8. Oxygen on the end also would need 6. So we used 4 electrons in those 2 initial bonds. We have 12 electrons left. We started with 16 total. Again, we used 4 in those 2 bonds. We have 12 left, but we need 16 to complete the octet. So we are 4 electrons short, so that means we need 2 more bonds. Now, normally, right, we would say, okay, well, we're just going to do a double and a double. So we're going to start there and look at our formal charges and see if that's actually correct. All right, so I'm going to start by putting a double on the nitrogen and then a double on the oxygen. Then to complete the octet, nitrogen in the center is done. It has 8, but the terminal nitrogen and oxygen would both need 4 more to get to 8. So if I just look at this real quick, 2, 4, 6, 8, 10, 12, 14, 16 electrons have been used, and everybody has the octet. So that looks like it should be a good structure. When I look at my formal charges, however, the formal charge, I'm going to just put underneath it here in red, we take the number of valence electrons, which for nitrogen is 5, and we subtract 1, 2, 3, 4, 5, and 6. So 5 minus 6 means this would have a formal charge of -1. The nitrogen in the center also comes in with 5, and we've assigned it 1, 2, 3, 4. So 5 minus 4 is a +1. And then the oxygen on the end, it comes in with 6, and 1, 2, 3, 4, 5, 6. 6 minus 6 means it has a formal charge of 0. So with formal charges, we try to avoid a couple of things if we can. Typically, we don't want a negative next to a positive, but usually the way we do that is by moving a lone pair into a bonding pair, and that would mean we would have to expand the octet. And the nitrogen can't expand the octet because it's in row 2. It doesn't have any d orbitals to tap into. So we're probably going to be stuck with a minus and a plus right next to each other, right? However, the element that has the negative formal charge should be the more electronegative element. That makes sense, right? So when I look at my periodic table, oxygen is more electronegative than nitrogen. So this is probably not the correct structure for N2O. And, you know, we go back to what we did. We knew we needed 2 more bonds, so we made a double and a double. But this is actually telling us that we should have instead done a triple and a single, right? And so let's see how that improves the formal charges. So nitrogen is going to be triple bonded to the nitrogen, and then a single bond to the oxygen on the end. So now the single bond oxygen would need 3 lone pairs to complete the octet. Nitrogen in the center is good. It has 8, 2, 4, 6, 8. And then nitrogen on the end with the triple bond would need 1 lone pair to complete the octet. So nitrogen 2, 4, 6, 8, nitrogen 2, 4, 6, 8, oxygen 2, 4, 6, 8. So everybody has the octet. Now if I look at the formal charges, Nitrogen comes in with 5. We've assigned it 1, 2, 3, 4, and 5. So 5 minus 5 is 0. Nitrogen in the middle hasn't changed. It came in with 5. We've assigned it 4. 5 minus 4 is a positive 1. And then oxygen comes in with 6, but now we've assigned it 1, 2, 3, 4, 5, 6, and 7. So 6 minus 7 means we've got a negative 1. So overall, it doesn't look like a huge improvement on the formal charges, but what was important here was that we had the more electronegative oxygen carry the negative 1 formal charge. So this is going to be our final structure for the N2O. All right, so we end up with a triple bond and a single bond. All right, in terms of exceptions, there isn't resonance here because this isn't a resonance situation. If the formal charges change, right, that means that's not resonance. Resonance is when you have like the same terminal elements and one has a double, one has a single, and then you could move those back and forth. But that's not what this is. So it's not, there's no resonance here. We do have the exception in the sense that we've got a triple bond, right? That is kind of unique. So we do have a triple bond here. All right. And the octet rule has still been satisfied. So the only thing we have here that is sort of special is the triple bond. All right. But everybody has the octet 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. You couldn't expand the octet for any of these anyway because both nitrogen and oxygen are in row 2. So they don't have d orbitals to tap into. And always just double check. There should be 16 electrons here. 2, 4, 6, 8, 10, 12, 14, 16. All right, so that would be the Lewis structure for N2O. All right, next one is Boron Trifluoride Bf3. All right, and so for this one, fluorine is our most electronegative element. It can never go in the center, so we know the boron would go in the center. All right, and then we're going to put fluorine on 3 sides. Doesn't matter which 3 you pick. All right, and then I'm going to go count my electrons. So my valence electrons, boron is group 3, and each of those fluorines brings in 7. 7 times 3 equals 21, not 7 times 21. So, sorry, that looks like an F, but that's 7 times 3 equals 21. 21 plus 3, we've got 24 total electrons to work with. All right, we've used 6 in those 3 bonds, so we have 18 electrons left. All right, when I draw my circles, the fluorines both need 6 more, not both, but all 3 of them would need 6 more to complete the octet. And then with boron, it looks like it would need 2 more to complete the octet. But boron is a sort of important exception here, and we can't make this work with a perfect octet because what we're going to find is we would be 2 electrons short, which would mean we'd have to make a double bond here. And when we do that, fluorine can't expand the octet, so fluorine would end up with a formal charge of positive 1. And that's not possible. It's the most electronegative element we have, can't end up with a +1 formal charge. And boron is an exception to the octet rule. It typically only does 3 bonds, so we can't complete the octet for boron. So boron is exception to the octet rule. All right, so we're not going to complete the octet for boron. Instead, we're going to just complete the octet for each of the fluorines. So 2, 4, 6, 8 to finish out each of the fluorines. All right, we're going to make sure we have the correct number of electrons here, 24, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And now at this point, if I look at my formal charges, the fluorine comes in with 7. We've assigned it 2, 4, 6, and 7. So now the formal charge is a 0. The fluorine also a 0, right? And then the boron comes in with 3, and we've assigned it 1, 2, and 3. All right, so all of my formal charges are 0, which is good. So this is our structure for boron trifluoride. So that's boron is always an exception that's outlined in textbooks, right? That it is an exception to the octet rule. Hydrogen, right, also follows is an exception. It's the duet rule, but boron, 3 bonds usually does it, so it only goes to 6. All right. Then if we look at nitrate, NO3 -1, center element here is going to be nitrogen, and we're going to single bond oxygen on any 3 of the sides that you want. And then when I go and look at my valence electrons, nitrogen group 5, oxygen group 6, but because this is a polyatomic ion with a -1 charge, that charge means that we have added an extra electron here, so we don't want to forget that. We got an extra one here. So we've got 24 total electrons to work with. All right, we've used 6 in the initial bonds, so we have 18 left, but I can tell that I'm going to need 6 on each of these oxygens and then another 2 on the nitrogen. So I can tell if I only have 18 left, but I need 6 plus 6 plus 6 by 2 plus 2, so I need 20. 18 left, 20 needed, I don't have enough. So nitrogen and oxygen, one of these is going to have to take a double bond. We're not going to have enough electrons to make it work with single bonds. So already in terms of exceptions, we can tell that we have a double bond here. We're not going to have any expanded octet because like we saw with the N2O, you can't. And then resonance is going to be important here. So because these are all terminal oxygens, that double bond can move between any of those 3 spaces. So the double bond could be on the left, could be on the bottom, could be on the right. And that's what resonance is. So it doesn't change the skeletal structure. It's still a nitrogen center, 3 oxygens, terminal. The double bond moves, and it doesn't change like the formal charges. One of the oxygens is going to have a formal charge of 0. The other 2 are going to be -1. And the nitrogen will be +1, but we'll look at that in just a second. So those are the 2 sort of special things about this nitrate. So to complete the octet, the oxygens with the single bond need 6 more electrons to complete, to go to 8. Nitrogen is good in the center, it has 8, and then the oxygen with the double bond needs 2 more lone pairs to complete the octet. Because this is a polyatomic ion, we put it in brackets, and we indicate overall it's a -1 charge. And then when I look at my formal charges here, this oxygen comes in with 6. We've assigned it 1, 2, 3, 4, 5, 6, 7. So it's got -1. And then same with the oxygen on the bottom. Oxygen with the double bond, it comes in with 6. We've assigned it 1, 2, 3, 4, 5, 6. So formal charge has gone to 0. Nitrogen comes in with 5, and we've assigned it 1, 2, 3, 4. So 5 minus 4 means it's a +1. Again, normally when we have a plus next to a minus, we try to fix that. I'm going to use my pencil so I can erase it. And the way that we fix that is we take a lone pair on the terminal element and move it into a bonding pair. And that'll fix the formal charge of +1 next to -1. The reason why we can't do that though is that if I put that lone pair into a bonding pair, this nitrogen would then have 2, 4, 6, 8, 10 electrons around it, and nitrogen cannot expand the octet. So the only time you have that option of improving the formal charges with a +1 next to a -1 is typically by expanding the octet on the center element, and we can't do that here. So the sum of my formal charges, +1, -1, -1, overall, I have a -1 total, which matches the charge on the polyatomic ion. So formal charges either have to sum to 0 if you have a compound, or they have to sum to the charge on the polyatomic ion. So in this case, -1. All right, so resonance, again, double bond can float between any of those 3 terminal oxygens. And then we ended up with a double bond because that was the only way to make the total number of electrons work. Making sure we have 24, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. All right, last one on the page, we've got carbon tetrafluoride, Cf4. All right, center element here is definitely going to be the carbon. Least electronegative always goes in the center. I'm going to put fluorine on all sides. All right, when I go and count my valence electrons, carbon comes in with 4. Fluorine each comes in with 7. So 28 plus 4 is 32 total electrons. All right, I've used 8 in those 4 initial bonds. So I've got 24 electrons left. All right, and when I look here, carbon is done, right? It has 2, 4, 6, 8. And each of those fluorines would need 6 more to complete the octet. So 6 times 4 is 24. So that means we don't need any double bonds here. We're just going to place the lone pairs on each of the fluorines to complete the octet. Again, carbon is done. It has the 4 bonds, so that's 8 for the carbon. All right, and then if I look at my formal charges, carbon comes in with 4, and we've assigned it 1, 2, 3, 4. So formal charge on carbon is 0. Each of the fluorines brings in 7, and we've assigned it 2, 4, 6, and 7. So 7 minus 7, these each have formal charges of 0. So we have the correct structure. Octet rule is satisfied for everything. Again, nothing here could expand the octet anyway. No double bonds or triple bonds. So nothing special in terms of exceptions to any of the rules that we remember from intro. So that is the final structure for carbon tetrafluoride. All right, the next page, we have bromate, which is BRO minus 3. So center element here would be the bromine. And we'll put oxygen on 3 sides. When I go and count my valence electrons, bromine comes in with 7. Each of the oxygens comes in with 6. And again, we've got a charge on the polyatomic ion of -1, so I got to factor that in. So 7 plus 18 is 25, plus 1 more is 26 total valence electrons. All right, so just making sure I did that right. Okay, so 26. All right, so I've used 6 in those initial bonds, so I take those out. I've got 20 electrons left. When I look at who needs what, each of the oxygens here has 2, so they would each need 6 more. I'm just going to use pencil kind of lightly so I can erase it. And then the bromine, 2, 4, 6, would need 2 more. So I had 20 left. 20 would be needed to complete the octet, so that makes this look like I don't need any double bonds, right? So this actually looks like it's going to be the correct structure. So I'm going to erase my valence, or how many needed. All right, and I'm going to put 3 lone pairs on each of the oxygens to complete the octet, and then 1 lone pair on the bromine to complete the octet. And that looks like that should work, right? 26 electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. There's 26. Everybody has an octet, so everything looks good. But now let's look at the formal charges. So each of the oxygens, right, they all are in the same situation. They come in with 6 valence electrons, and we've assigned each oxygen 1, 2, 3, 4, 5, 6, and 7. So always each lone electron plus half of the bond. So 1, 2, 3, 4, 5, 6, 7. So this oxygen has a -1 formal charge, and so do the other 2 oxygens as well. When we look at bromine, bromine comes in with 7 valence electrons, and we've assigned it 1, 2, 3, 4, and 5. So 7 minus 5 is a 2. So in that scenario, right, again, we don't want negative next to positive. We can start moving that lone pair on the terminal element into a bonding pair, but only if we can expand the octet on the bromine. And the bromine, we can. It's in row 4, so it does have d orbitals that it can tap into. So we're going to take one of the lone pairs on one of the terminal oxygens and move it into a bonding pair. And we're going to do that 1 more time. And the reason why we know to do it twice is because bromine is a +2. So that means we need to do this twice. All right, so what we're going to end up with here, and I'm going to have to probably show it up here so I have enough room, is we're going to leave one of the oxygens with just a single bond. That's going to carry the formal charge of a -1. The bromine in the middle is going to keep that lone pair. But now on the right, we're going to have oxygen with a double bond. And on the bottom, we're going to have oxygen with a double bond. All right, and then there would be my charge of -1. So this right here would be the bromate Lewis structure. This would be my final answer for that. So now when I look at my formal charges, the oxygens with the double bond, they still have followed the octet rule, 2, 4, 6, 8, right? Oxygen is still stuck at 8. But the formal charge would be 6 minus 1, 2, 3, 4, 5, 6. So 6 minus 6 gives that formal charge of 0. Same for the other oxygen with the double bond. The bromine in the middle, right, comes in with 7, and we've assigned it 1, 2, 3, 4, 5, 6, 7. So 7 minus 7 is a 0. And then the oxygen with the single bond, that's the one that has the -1 formal charge. So we could expand the octet here. We got our formal charges all to 0, which is ideal, except for one element, which is the -1 single bond oxygen. But we knew we had to have something carry a -1 because our charge is -1. Now, we didn't want to do another lone pair to the center because bromine then would have had the -1 charge, and always the negative formal charge should be on a terminal element because those are the more electronegative elements, right? So if something has to carry a -1, it has to be one of the ends, right? This would be another situation where you could have resonance, right? Where did you put the double bond? Well, we could have put it here, we could have put it here, right? You can move it. We've expanded the octet on the bromine, and we have double bonds. So there's kind of a lot going on with the bromate polyatomic ion. All right, but this is our final Lewis structure for the bromate, right, where it has 2 double bonded oxygens and 1 single bonded oxygen. All right, so now let's look at the chlorite, ClO2 negative. All right, so let me draw my line. Okay, so we're going to start with chlorine in the center, oxygen on either side. When I look at my valence electrons, chlorine comes in with 7, and each oxygen 6, so that'd be 12 plus 7 is 19, plus an extra 1 for the charge, so we've got 20 total valence electrons. All right, so 20 total electrons. We've used 4 in those initial bonds, so we have 16 electrons left. All right, when I go and look, the oxygen with the single bond, right, both oxygens would need 6 more to complete the octet, and the chlorine would need 4 more to complete the octet. So 6, 4, and 6, that's my 16 that are needed, right? So again, like the bromate above, this looks like this is going to work pretty well by just placing our lone pairs. All right, so we're going to start there. We're going to put 3 lone pairs on each of the oxygens and 2 lone pairs on the chlorine. Right, and just count 20 electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. There's my 20. Everybody has an octet, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So that looks good. Now when we look at our formal charges though, oxygen comes in with 6. We've assigned it 1, 2, 3, 4, 5, 6, 7. 6 minus 7, -1. Same for the oxygen on the left. Chlorine comes in with 7. We've assigned it 1, 2, 3, 4, 5, and 6. 7 minus 6, +1. So like we saw with the bromate, we can make that better. So we're going to move one of these lone pairs into a bonding pair. All right, so I'm going to kind of start over here. We'll have our oxygen on the left. I'll have that one keep the single bond. And the oxygen on the right, I'll have it be the double bond. All right, and now what I can see is my formal charge of the oxygen with the double bond has gone to 0. 1, 2, 3, 4, 5, and 6. The chlorine has gone to 0. 1, 2, 3, 4, 5, 6, 7. And then the oxygen with the single bond has the -1. And again, we knew that that had to happen because overall the charge on the polyatomic ion is a -1. So again, we've got a double bond here. Since both terminal elements are oxygen, that means we have resonance. And we've expanded the octet on the center chlorine, which is possible because it is a row 3 element. So that is definitely doable because it can tap into those 3D orbitals. All right. That is your chlorite polyatomic ion. All right, now for the next one, we have arsenic pentafluoride. So arsenic's going to go in the center. And then normally what we saw was we would do only 4 bonds, right? That was what we started with intro, but this is going to be able to expand the octet. We know that because arsenic, right, is in row 4. So we're actually going to have 5 bonds here. So we're going to have a fluorine, 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 and then fluorine and fluorine. All right, so when I look at my valence electrons, arsenic is group 5, and each fluorine 7. So I have a total of 40 electrons here, right? We've used 10 in those 5 initial bonds, so we have 30 electrons left. If you were to ask yourself how many more does arsenic need, you would say it already has 10, so it doesn't need any more. And then each of the fluorines would need 6 more, so there's my 30 that I had left. So I'm going to place 3 lone pairs on each of the fluorines. And that'll complete the octet for the fluorines. Fluorine can't expand the octet. It's stuck to the octet, right, because it's a row 2 element. And if I look at my formal charges, each of the fluorines comes in with 7. We've assigned it 2, 4, 6, and 7. So all of the fluorines have a formal charge of 0. And the arsenic comes in with 5, and we've assigned it 1, 2, 3, 4, and 5. All right, so that is our Lewis structure for arsenic pentafluoride, right? So in this case, what we have is expanded the octet. But no double bonds needed, no resonance, anything like that. All right, then we've got the Selenium Tetrafluoride. So here, sorry, that was supposed to be TE, but I'll adjust. All right, so we'll put fluorine on 4 sides. So the tellurium, it is in the oxygen family, so it brings in 6 valence electrons. And then each of the fluorines brings in 7. So 28 plus 6 means we have 34 total electrons. We've used 8 in those 4 bonds. So we have 26 electrons left. When we look at the fluorines, they would each need 6 more. So 6, 6, 6, and 6 is 24. So if we subtract out 24, that means we have 2 electrons extra. And we know that they can't go on the fluorines because fluorines can't expand the octet. It's a row 2 element. So they're going to have to go on the tellurium, right? And we'll see with formal charges that that is okay. So we're going to fill the octet for each of the fluorines. We put those 2 extra electrons on the center tellurium. And just double checking, I should have 34 electrons here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34. And then all my formal charges, the fluorines are all 0. They came in with 7. We've assigned them 7. And tellurium is group 6, and we've assigned it 1, 2, 3, 4, 5, and 6. All right, so the special thing about this one is we have an expanded octet on the center element. All right, but no double bonds needed, no resonance or anything like that. All right, now a couple more here. All right, we have IF3. So I in the center, fluorine on 3 sides. All right, when I go and count my electrons, the iodine and the fluorine are all group 7. So we have 28 total electrons here. We've used 6 in those 3 bonds, so we have 22 left. And it looks like we would only need 6, 6, 6, and 2, which would be 20. So again, we're going to have an extra 2 electrons, right? But we're going to go ahead and complete the octet on the fluorine. All right, and again, fluorine can't expand the octet because it's row 2. So 28 total electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So there's 4 more. That means we're going to put 2 lone pairs on the center iodine. Looking at my formal charges, the fluorines are all 0. And then the iodine comes in with 7, and we've assigned it 1, 2, 3, 4, 5, 6, 7. So that's also a 0. So all my formal charges are 0. And again, what's kind of special here is we've expanded the octet. All right, so this was a little bit different, right? Kind of like what we saw with the tellurium and the arsenic. But also with the tellurium, you have an extra number of electrons. That's kind of unusual, right? So again, kind of going through the math, we started with 28. We used 6 in those 3 bonds, so we had 22 electrons left. And when we looked at it, it looked like 2, 4, 6 on each of the fluorines to finish, and then only 2 more for the iodine. So it looked like we only needed 20 to complete the octet. So we had 2 electrons extra. And again, when that happens, that goes on the center element. All right. Now, next one, we've got Krypton Difluoride, KrF2. So Kr, F, and F. And this is going to be another one. Whenever you've got those noble gases, you're going to end up with expanded octets. So I'm going to go ahead and complete the octet on the fluorines because you know with the fluorines you're stuck. It has to be 8. And now we're going to look at our number of electrons. So krypton noble gas comes in with 8. Each of the fluorines comes in with 7, so that would be 14. So we've got 22 electrons total. All right, so we've used 2, 4, 6, 8, 10, 12, 14, 16. We have 6 more. So we're ending up here with 3 lone pairs on the center of krypton. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22 total. So again here, we're going to have an expanded octet. And when I look at my formal charges, each of the fluorines are 0. They come in with 7. We've assigned it 7. And then the krypton comes in with 8, and we've assigned it 2, 4, 6, 7, 8. So also a 0. So all formal charges are 0. All right. The selenium hexafluoride. So selenium should go in the middle. And this one, we're going to see this is our max. We can do up to 6 bonds. And we're going to go ahead and complete the octet on the fluorine. All right, not to always use fluorine, but the reason why fluorine is nice is because there's no ambiguity. Like you can't expand the octet. So if you were, looking at anything with extra electrons, fluorine is good for that. You can't expand the octet on fluorine. You're stuck at 8. So when I count my electrons, selenium is group 6. Each of the fluorines is 7, so 6 times 7 is 42. So there should be 48 total electrons here. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. So there's my 48 total electrons. All of my formal charges are 0. The selenium comes in with 6. We've assigned it 1, 2, 3, 4, 5, and 6. All formal charges are 0. So again, the special thing here is that we have an expanded octet. All right. 2 more to go. All right, I have 5. So I is going to be in the middle. Fluorine on 5 sides. Right, we can go up to 6. We're going to go ahead and complete the octet for each of the fluorines. I shouldn't have put it there. Sorry. I'll just make the bond over there. My mistake. You don't really want to show a bond next to a lone pair. So pretend the bond is coming in on the bottom. Sorry about that. All right, and then each of the other fluorines, 3 lone pairs to complete the octet. All right, and looking at my total number of electrons, each of these come in with 7. So 6 times 7, again, we've got 42 electrons total. And we've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. So we've got 2 electrons extra, and that's going to go somewhere on the center iodine. Formal charge on all the fluorines is 0, and on the iodine, 1, 2, 3, 4, 5, 6, and 7. So all formal charges are 0. And again, what's special here is we've expanded the octet on the iodine. All right, so the reason why we keep seeing so many expanded octets is I organize these by the geometries, which we will see in the next chapter. So we'll kind of see why they're laid out this way. All right, so next one is the Krypton Tetrafluoride. Krypton in the center, fluorine. All right, and then I'm going to complete the octet for the fluorines. All right, and then we're going to go and count our electrons to make sure we have all of them in the compound, in the structure. So krypton, again, noble gas comes in with 8. Each of the fluorines brings in 7. 7 times 4 is 28. So I've got 36 total electrons to work with. 2, 4, 6, 8. I've used 32, right? 8 times 4 is 32. So I have 4 extra electrons. So I'm going to put 1 lone pair on the top and 1 lone pair on the bottom. So now I have 36 electrons. And again, what is special here is I've expanded the octet. All right, so formal charge, just to review that again really quick. You take your valence electron, so for fluorine that is 7, and you minus out 1 for each lone electron and 1 for each bonding pair. So basically you're taking the bond and splitting it in half. So one of those electrons counts for the fluorine and the other one counts for the krypton. So fluorine, 1, 2, 3, 4, 5, 6, and 7. So 7 minus 7 gives me a 0. And that's true for all of the fluorines. And then for the krypton, it comes in with valence electron of 8. And we've assigned it 1, 2, 3, 4, 5, 6, 7, 8. So 8 minus 8, again, we have a 0. So all formal charges are 0. It's a great indication that we have the correct structure. It's just we had to expand the octet. And again, the rule with the expanded octet is it just has to be in the periodic table a row 3 element or below. It has to be able to tap into d orbitals. So anything in row 2 cannot expand the octet. So that's what you want to remember there. The other thing that we looked at was occasionally, right, we need double bonds, resonance, right? So with your formal charges, if you can make them better by moving a lone pair into a bonding pair, and that only can happen if your center element can expand the octet, you can do that if that improves your formal charges. And then when you end up with a double bond and the same sort of terminal elements, then you can have resonance. All right, and again, you can only move the bonding pair to, the lone pair to a bonding pair if you can expand the octet. All right, so we looked at all of things, Lewis structures in this video. On the next video for chapter 11, we're going to start assigning the geometries and looking at the orbital hybridization.